Hi, I'm Hao Shen. I'm a PhD student from the University of Pennsylvania. Today, I'm going to present Declarative Smart Contracts, where we propose a declarative domain-specific language for smart contracts. This is a joint work with my colleagues from UPenn and Simon Fraser University. First, smart contracts are programs stored and executed on blockchains. Their typical applications include tokens, auctions, and financing applications, etc. On the right-hand side of the slide are the top Ethereum tokens. You see there are billions of dollars worth of tokens being traded every day. Bugs in smart contracts have caused significant financial loss. So it's important to ensure smart contracts are implemented correctly. This is how smart contracts are implemented today. They are written in a language called Solidity. It's an object-oriented programming language, very similar to Java. As you can see on the left-hand side of the slide, here is an example contract called the wallet and its definition. A contract is like a class in Java, and contract deployment is like class instantiation. And within the contract definition block, first we have contract state declaration, and then function definitions. And here in Solidity, we make the distinction of two special functions. First are transactions. They are public functions that alter the contract states. And views are public functions that do not alter contract states. And this distinction is made because updating the blockchain is very expensive due to the underlying consensus protocol. So why do we need a new language? It's because existing smart contract or application work, most of them focus on generic and low-level properties. For example, reentrancy attack, which typically leads to you sending money multiple times, thus losing your money. And integer overflow, it's a typical program property to be verified generally. But there's not so much work on contract-specific and high-level properties. For example, in this wallet contract, do all the account balances add up to the total supply of tokens? Therefore, we need a high-level and executable language to ease the specification and implementation of smart contracts. With this idea, we present Decon, a declarative language for smart contracts, and it provides runtime verification for safety properties, automatic code generation, and an intuitive debugging interface via data provenance. So why do we take this declarative approach? It is based on the observation that smart contracts are managing relational databases. Transaction records are stored as relational tables on blockchains, where every row is a transaction and each colon is a transaction parameter. The second observation is that smart contract operations and contract level properties can be naturally expressed as relational constraints. For example, if I want to see the balance of a particular account, say 0x01, I would pull the transfer record where it is the sender and another group of transfer record where it is the receiver. And I sum up the amount of these two groups of transfer records to get the income of 0x01 and the expense of it, and I do a subtraction and I get the balance of this account. Similarly, for the property that all account balances add up to total supply of tokens, it can be specified as the following query, where you first sum up the amount colon in the balance table and you compare it against the total supply table and see if they are equal. And the correct contract, in the sense, is supposed to have this query always being empty. With these two observations, we realize that smart contracts can be implemented declaratively, the same way as database queries are specified in Datalog. Next, I'm going to show you in detail how to specify smart contracts in Decon. If you know Datalog already, it will look very similar to you. So again, we have this example wallet, and it's a smart contract that manages digital tokens. It supports 3 kinds of transactions: mint, burn, and transfer. Each kind of transaction records are sorted in the relational table here. And a decon contract consists of 2 major components. First is relation declaration. Here in this example, we're showing 3 special relations, where you have a table name, and then in the parentheses, you have colon names followed by their types. And we're showing special relation here with the receive prefix, which means that they are transaction event triggers. And these special relations will be translated into a transaction interface where function arguments are the relation schema, and it returns a Boolean value indicating the success of the transaction. Other special relation annotations are, for this total supply relation is annotated with a star, which means it only has 1 row. For the balance of relation, it has a bracket with a number 0 in it, and 0 is the index for its primary key colon, which is P here, and a primary key uniquely identifies a row. Inserting a row will update a row with the same primary key. And then next we have a public declaration of these 2 relations. It means that public interface will be generated for users to query the content of these 2 tables. And the second main component is the rules. And here we also make a distinction of 2 kinds of rules. First are the transaction rules, which are the rules with a transaction event trigger. For example, R1 specifies the processing logic for the mint transaction. Here, the predicate receive mint here is triggered to true when it receives the transaction to mint and tokens to address P. And rest of the rule are the condition on which this transaction can go through. And here in R1, it says that the message sender should be the contract owner and the transaction amount should be greater than 0. And if everything is checked through, it adds a new row into the mint table. Next are the wheel rules, which are rules other than the transaction rules. So R4 shows the definition for the relation total supply, which is the sum of all mint transaction amounts subtracted by the sum of all burn transaction amounts. And R10 and R11 shows the decon syntax for doing the sum aggregate on the mint and burn table. Here is the complete decon program for the wallet contract. Next are the property. Similarly, properties are specified in the same way as rules, but with a violation annotation. And here in R14, the negative balance relation is defined as the entry in the balance of table where n is less than 0. And safety means that the violation relation are empty after every transaction commit. And with this annotation, decon will generate the following instrumentation block to check the violation on runtime. Finally, I'm going to show you the evaluation. We measure 2 kinds of overhead. First is the executable code generated from decon. How does it compare to the reference Solidity implementation? Second is the runtime verification overhead. And we use gas, a special measure used by the Ethereum community to measure the execution cost of smart contracts. So here is the main result. Here on 5 representative contracts and all their supported transactions, we see the gas cost of decon and the reference contract. The difference varies quite a lot. Sometimes it's better, sometimes doing worse, but at the medium, it's 14% overhead over the reference Solidity implementation. Here is the runtime verification overhead. Again, the overhead varies quite a bit, but at the medium, it's 16%. In summary, decon shows that Smart contracts can be naturally expressed as relational queries, and Decon can automatically generate solidity code from declarative rules, verifies safety properties during runtime, and supports data provenance for intuitive debugging. Our evaluation shows that Decon has moderate overhead over reference solidity implementation. In the future, we plan to explore static verification of Decon contracts and gas optimization for the Decon compiler. Please check out our work at the GitHub repository. Thank you.